right? I think when we are here, so let's get started with today's class. So if we recollect, we were looking at steps involved in constructing the root locus, and we essentially studied the first three steps, right? So we broadly observed that the root locus is used to capture the the locus of the closed loop poles as we vary a system parameter, and we essentially looked at a standard form for the open loop transfer function, and as a parameter k is varied. The question becomes, like how do the closed loop poles vary in relationship with the open loop poles and open loop zeros. So in that regard, we considered the standard transfer function, open loop transfer function, k times s plus z1 all the way to s plus z divided by s plus v1 all the way to s plus vn, and 1 plus that is equal to 0, k being a positive parameter. That's the first case we have started off with. And we completed three steps, right? So the first step was to locate the open loop poles and open loop zeros in the S-plane. The root locus will have n branches, and each branch will start from one open loop pole as k starts from 0. And m of those n branches will end at open loop zeros, and the remaining n minus m will go to asymptotes or will go to infinity along asymptotes, right, as k tends to infinity. Then we locate the root locus branches or paths which lie on the real axis. We do that by taking a test point and counting the number of real open loop poles and real open loop zeros that lie to the right of this test point. And if that number is odd, then that point lies on the root locus. As we observe, that odd number comes because of the angle condition, right? Which necessitates that the face be an odd multiple of 5, right? For a value of s to be a closed loop. And the third step was to determine the asymptotes of the root locus, which applies only when m is less than n. And then, like we saw that the angle made by the asymptotes in the positive real axis is plus or minus 180 degrees times 2k plus 1 divided by n minus m, and the point of intersection was sum of open loop poles minus sum of open loop zeros divided by n minus. Okay, so this is where we stopped, right? So now we briefly started with the fourth step. Like we briefly understood what is a breakaway point and a break-in point, but let's recap, right? So that like we go from there, right? So if we look at a breakaway or a break-in point, so we saw that we will have, where did I draw that figure? Yeah. So essentially, if we have two open loop poles on the real axis, like in this example, -4 and 0, one branch starts from -4 and goes towards the right. One branch starts from 0 and goes to the left. At some point, they need to intersect on the negative real axis, and from there, they branch out into the complex plane. Okay, that is a breakaway point. Similarly, if we look at this particular figure, if at all, like in this example, we don't have that, but if we had, let's say, two open loop zeros on the real axis and two branches are terminating at them, right, as indicated here, very likely that two branches may come from the complex plane, intersect at a point, and then break into the real axis. Okay, so those are what are called breakaway and break-in points. Now, what is a common feature about breakaway and a break-in point? Please note that these are points where two branches of the root locus intersect each other. That means at that value of k, there is going to be a repeated pole as far as the closed loop poles is concerned, right? Because each branch we know that is a trace of one closed loop pole, right? So when two branches of the root locus intersect, that means at that point there is a repeated closed loop pole. Okay, so we are going to use that characteristic to derive the step. Okay, so please remember that. Let's go and look at this. So in step 4, we start here. So this is our open loop transfer function k times s plus z1 plus s all the way till s plus zm divided by s plus p1 all the way till s plus pn. So we call the factor s plus z1 all the way till s plus zm as some a of s. S plus P1 all the way till S plus Pn as some B of S. Okay, so what we are doing is that like the open loop transfer function G of S, H of S, we are writing as K A of S divided by B of S, just for simplicity of notation. Okay, nothing more than that. Okay, so we have consequently we have the closed loop characteristic equation as 1 plus K times A of S divided by B of S equals 0. Now, before we come here, let's look at this particular example, right? So if we look at this particular example, right, and then like we essentially then apply the step to the root locus example that we are studying, things will become clear. So let's consider a polynomial s plus 1 whole square times s plus 2. So the roots of the polynomial are -1, -1, and -2. Okay. So now, in this case, which is the repeating root? The repeating root is
-1.
-1, right? So by definition, the root of a polynomial is the value of s at which the polynomial will become 0. So please note that, let's say we substitute -1 or -2, d of s is going to be 0. That's the definition of root of a polynomial. However, when there's a repeating root, let's say we take the derivative of the polynomial with respect to s. So we take the derivative of t of s with respect to s, we get 2 times s plus 1 times s plus 2. Okay, when we take the derivative of s plus 1 whole square. Then if I take the derivative of s plus 2, I just get 1. So I just settle with s plus 1 whole square. So we use the product rule for differentiation. Now something becomes interesting, right? Since -1 is a repeating root which repeats twice, the first derivative of d with respect to this polynomial with respect to s is also 0 at -1. However, when we substitute -2, the derivative is not 0. Okay, so this is a unique property which happens or which comes into play when there is a repeating root. Okay, so I hope this point is clear. So, in other words, if a root of a polynomial repeats twice, not only is the polynomial 0 at that value of s, but the first derivative of the polynomial with respect to 0 is also s at that value of s. Okay, so you and I are going to leverage this concept, okay, to our advantage. So how are we going to do this? We are going to apply that to 1 plus k times a s by b by s. So what we do is that, like, when we take the derivative, 1, it's constant, right? So the derivative is 0. Then we are left with k times a of s by b of s. How do I take the derivative of a of s by b of s? We use the ratio polynomial, sorry, differentiated derivative of ratios, right? So what we do is that we write the denominator square, and then in the numerator, first we differentiate the numerator multiplied by the denominator factor minus the numerator multiplied by the denominator factor. Okay, so this is how we calculate the derivative of ratios of polynomials, right? Or functions, what we call as a p by q rule and so on, right? When we learn calculus. Okay, so so essentially this becomes equal to 0. Obviously, b of s is what to say. We can take it to the other side. K is not 0. So what you and I get is a prime s b of s minus a of s b prime s is equal to 0. So in other words, if we solve this particular equation, figure out values of s. They are the potential values of s where there may be repeating closed loop poles. Okay, so they may be potentially breakaway points or break-in points. But then the best way to check is we come back to the closed loop characteristic equation, which is 1 plus k times a of s by b of s equals 0. From here, we can see that k I can write it as minus b of s by a of s. How did I get it? I just took minus 1 to the other side and then cross multiplied, right? So I get this. So we substitute the solution into this, and only when k is greater than 0, because that is the premise under which we are constructing these steps, right? Only for those values of s where k is greater than 0 or actual breakaway or breaking points, okay? So some will write the same equation as b prime as a of s minus a prime as b of s, okay? So that's how we would have written in the notes and many textbooks, okay? So it's the same equation, right? So we have just taken the factors to the other side, okay? So I hope it's clear how we got this formula, okay? So now let's apply it to our example. So in our example, if we recall, the open loop transfer function was k divided by s times s plus 4, right? So what do you think is a of s? If you compare with this,
It is K, sir.
it is 1, right?
Okay. Sorry, sir.
Look at this
Sorry.
canonical. Yeah, k times a of s is k, correct, right? But a of s then will become 1, okay? So yeah, so this is just another canonical form that we are using, Roshan, okay? So a of s becomes 1. So what will be b of s?
S plus S plus 4. S into S plus 4.
So I'm just going to write it as s squared plus 4s, okay? Just expanding it, right? So yeah. So from here, what will be a prime of s?
It will be 0, sir.
0, right? Because there is no s term, okay? So what will be b prime of s?
2S plus 4.
So we can see that that's what we have written here. So consequently, this equation here will become 2s plus 4 times 1 minus 0 is equal to 0. So consequently, we will get s to be equal to minus 2. Okay, so this is the potential breakaway point. Okay, so once we get the solution, we add a subscript b just to show that this is a potential breakaway point. And then we go and calculate the value of k at this potential breakaway point. Okay, so so essentially we go ahead and calculate minus of s squared plus 4s, that is b of s, a of s is 1 at s equals minus 2 or sb equals minus 2. So if we substitute it and calculate it, we see that in the numerator, s squared plus 4s becomes minus 4, but then there is a minus outside. Okay, so minus of minus 4 becomes 4. So, and that is positive. So we are having SB equal to 2 minus 2 as a breakaway point. Okay, so that's what happens in this particular example. So, sorry, this is example of break-in point. So, sorry, not this. Okay, so in this particular example, what has happened is that like this is what happens, right? So essentially one branch starts from minus 4, another branch starts from 0. At minus 2, they break in and then they go out, okay, they branch out. And the value of k at the breakaway point is 4, okay? So I hope it's clear how we did this stuff, all right? Okay. So any questions on this fourth step, you know, how to calculate breakaway break-in points? Okay. So anyway, we'll be doing more examples. Okay. So as we do more examples, these things will become much clear. All right. Okay. So now comes the next step. Okay, the fifth step. Once again, root locus construction is very methodical. Okay. So what we need to do is that see, many of these steps, as I told, you know, like nowadays, you know, we are learning so that you and I get an intuition when we do control design, right? The actual root locus construction, you know, like if you use the R locus command in MATLAB and all, we will be able to generate within a matter of few seconds. Okay. So, but still, it is important for us to know the concept. That's why we are learning it. Now, what is the fifth step? The fifth step, once again, we do not read what is there within the parenthesis at the top, you know, like in the italics font. We locate the angle of departure from an open loop complex pole, right? So how do we calculate it? The angle of departure from an open loop complex pole is 180 degrees minus sum of the angles made by the vectors from other open loop poles to this pole, plus sum of the angles made by the vectors from open loop zeros to this pole. Okay, so how did we get this formula? Once again, let's understand what happened here. Let's understand the intuition behind this. Please, point number one, please note that, step number 5 applies only if you have complex open loop poles and complex open loop zeros. Okay. So in the particular example that we are considering, so what is the particular example that we are doing to understand root locus? The open loop transfer function is k divided by s times s plus 4. Okay, and k being a positive number. Okay, so we can immediately observe that there are no complex open loop poles, no complex open loop zeros. So in such a case, if we encounter such a problem, we can just write that this step does not apply to this problem. Okay. But then we are learning the general concepts. Okay. So let's figure out why this is the case. All right. So let's say, for the sake of learning, we essentially consider a complex open loop pole, which is here. Okay. So obviously the conjugate is also an open loop pole. So when we have an open loop pole, as we know, one branch starts from an open loop pole, right? The question is, which direction does the branch start? That is what is called as angle of departure. Okay, so now I hope the meaning of the word angle of departure is clear. When we had the open loop pole on the real axis and which is not repeating, we already observed that it can go either to the right or to the left. That means angle of departure was only 0 degrees or 180 degrees. But then if we have a complex open loop pole, it can go in any direction, right? That is the purpose of this step, okay? To calculate the angle of departure for a complex open loop. How do we do that? Still, please note, the open loop transfer function has to satisfy the angle condition, right? For the particular value of S to be an closed loop pole. So what we do is that, let us say without laws of generality, there is an open loop pole here, open loop pole here, and an open loop zero here. We draw vectors from other open loop poles to this particular pole. Okay, that means we draw one vector which makes an angle phi 1. We draw another vector which makes an angle phi 2. And then from this open loop zero, we draw another vector which makes an angle theta 1. Okay, with the real axis. Now, all these angles should satisfy the angle condition in the direction in which the branch starts from the open loop, complex open loop pole, which is here, right? And that is the reason why the angle of departure comes out to be 180 degrees minus phi 1 plus phi 2 plus theta. So phi 1 plus phi 2 is the sum of the angles made by vectors drawn from other open loop poles to this complex open loop pole. And theta 1 is the sum of the angle. There is only one open loop zeros in this example, right? The angle made by the open loop zero or the vector drawn by the zero to this particular pole under consideration. Okay. So this step applies only when we have complex open loop poles. Okay? We calculate the angle of departure using this concept. Similarly, we calculate angle of arrival.
I'm
yes,
sorry,
please.
sir. Just sir, what is theta 1, sir? Can you repeat, please, if possible, sir? Please.
Theta 1, see, I'm just considering a generic example, Roshan, without laws of generality. I have arbitrarily chosen an open loop zero. Let me redraw this figure. So let us say I have this, right? So what I do is that to figure out the angle of departure from this pole, I draw vectors from other open loop poles. Let me call this angle as phi 1, this angle as phi 2. Okay. And then I draw vectors from open loop zeros to this pole. Let's call this angle as theta. Okay. So that's what it is. Okay. So phi means is a symbol I am using to denote angle made by vectors drawn from other open loop poles to this open loop pole. Theta denotes the angle made by the vectors drawn from open loop zeros to this pole. Okay, I hope that is clear. All right. The formula comes because of the angle condition. That's all there is. Is it clear? No, sir.
Right, sir. Clear, sir. Clear.
Yeah. Similarly, of course, as I told, in this particular example, this step does not apply because there are no complex open loop holes, no complex open loops. Now, if you have an an open loop 0 which is complex conjugate, then as we know, one branch is going to end at the open loop 0, right? So then the question is which direction it will come in, right? And that is why the corresponding calculation is what is called angle of arrival. So when we have a complex open loop 0, we call it as the angle of arrival calculation on this complex open loop 0. So that is exactly the complement of this. That is 180 degrees minus sum of the angles made by other open loop zeros or vectors drawn from other open loop zeros to this open loop zero, plus sum of the angles made by the vectors drawn from all open loop holes to this particular zero. Okay, so you can see the symmetry in the formula. Okay, or the what to say? Essentially, I would say, like similarity, okay, in the formula used for calculating angle of departure from a complex open loop hole and angle of arrival at a complex open loop zero. All right. Okay. So I hope this step is clear. Okay. This is step number 5. All right. So when we do not have a complex open loop 0 or a complex open loop hole, step 5 does not apply. All right. So that is the bottom. So is step 5 clear to everyone? So once again, as we keep doing problems, it will become much easier, right? So see,
sir,
yeah.
can I stop
Sir,
to
Yeah, please go ahead.
Yeah, because if you want, you can ask first.
Okay, thank you. So, sir, for this, can you go back to that slide, sir?
Okay. Yeah. Mhm.
Yeah. So, in our first example, when we are having this from open loop 0 to open loop pole, theta 1 angle I am talking about.
Uh-huh.
So, typically for open loop for zeros, we have arrow arriving towards the 0.
That is when you want to calculate which branch arrives at the 0. But here you are calculating how the branch goes away from the open loop pole because, okay. So anyway, since this question has come, let me go a little bit more into theory. Okay. So since you have this question has arisen, so let me write down the general example, okay, which I have plotted here, right? So I have three open loop holes. Is that correct? Because like one open loop 0, right? So let's call this minus Z1, minus P1, minus P2, minus P3. Okay, all right. Okay. So now, what is the angle condition? Because so it should be angle of K is 0. It should be angle of S plus Z1 minus angle of S plus P1, right? Sorry. 1 minute, like 10 plus angle of S plus P2 plus angle of S plus P3 should be equal to plus or minus 180 degrees times 2K plus 1. I hope this fine, Vikas, right? I hope till here we are okay, right? Okay. Now,
Yes,
you and I need to find the angle of departure. Okay, so let me zoom into P1. Let us say I take a test point ST, which is very, very close to minus P1. Okay, I draw a vector, right? So this is the angle of departure, theta D, from this P1. Okay, so this vector is going to be ST minus of minus P1, which is ST plus P1. Okay, so that is what you and I want, the angle of that. All right. So now let's go back to this expression. So I choose this test point ST plus Z1 minus ST plus P1 plus ST plus P2 plus ST plus P3. For the sake of simplicity, we just take 180 degree, right? Instead of writing plus or minus 180 times 2K plus 1. Then what do you and I get from this equation? or let's say plus or minus 180 degrees, right? To 2k plus 1, doesn't matter, right? So we want ST plus P1. So that, how do I get plus or minus 180 times 2k plus 1 minus, if I rearrange the equation, I'll get ST plus P2 plus ST plus P3 plus angle of ST plus Z1. I hope till here I'm clear, because
Yes, sir.
now let's interpret. Okay, so this I will just take as 180, for the sake of calculations. Okay, so you and I can take it as plus or minus 180 or plus or minus what to say 180 times 3 is going to be 540 and so on. Anyway, things are going to be periodic. Okay, so no problem about that, right? So now, what is ST plus P2? Let's zoom in once again. Where is ST? ST is infinitesimally close to this minus P1. So if I draw ST plus P2, angle of ST plus P2 is going to be equal to angle made by a vector drawn from minus P2 to ST. Okay, that's how you and I should interpret. And what is the vector drawn from minus P2 to ST? It is this vector, right? Is it correct? Because it is ST is very close to minus P1. So it is almost the same as drawing a vector from minus P2 to minus P1. Okay. So now I hope you're getting the answer to the point, your question, Vikas, right? So what will be ST plus Z1? Let's figure it out. It will be ST minus or minus. What is this vector? It is the vector drawn from minus Z1 to ST or minus P1, right? So now I hope it's clear how we got theta, right? Sir?
Yes, sir. Clear. Thank
So,
you.
yeah. Yes, sir. Yes, sir. Prem, you had a question? No.
Clear, sir.
Yeah, the questions were on the same lines only.
Same line. Okay. Yeah. So, yeah. All right. So once again, so kindly watch those videos on control systems. I think there I would have gone in depth. So here I'm just only, summarizing the main steps, so that we apply them. But I'm very happy that your batch is asking all these questions. Okay, that shows, that's a very positive indicator. Okay, yeah. All right. So, and please keep asking these questions so that I will also remain sharp. Okay, so I should also be able to answer these questions. Okay. All right. So now that we have completed step 5, let's go to this last step, okay, which is what is called as determining the crossover points. Okay, that is, we need to figure out where the root locus may cross the imaginary axis. Now, why do we? Why is this step important from a practical perspective? Right. Let's figure it out. So, where is this step? Okay. So if we look at this S plane, we know that this is the left of plane, this is the right of plane, right? And the imaginary axis is the boundary or the stability boundary, right? It separates the left of plane and the right of plane. Now, why do you think the imaginary axis becomes important here? Or why are we worried about the root locus branches? When do they cross the imaginary axis?
Because if it is crossing the imaginary axis, at that point it will become unstable. System might become unstable.
It can, very good. It can go both ways. Right? That is, if I go from LHP to RHP, I need to cut the imaginary axis. Then I will go from stable to unstable. If it's the other way around, I may come from RHP to LHP. So for a physical system, as a design engineer, I need to know if at all there is a case where for some value of this gain K, which may be a controller parameter, am I going to cut the imaginary axis? Okay, then I would be careful, right? Such points where we cut the imaginary axis are what are called crossover points. Okay, so once again, all these terms have a lot of intuition, right? Why do you think it's called crossover?
Because it is moving from stable to unstable zone or vice versa.
It is crossing over from LHP to RHP or vice versa, right? Yeah, that's why it is called crossover point. Okay. So now, how do I figure out the crossover point? Okay. So please note, in general, S is a complex variable which will have the structure of sigma plus j omega. But on the imaginary axis, sigma becomes equal to 0. So S equals j omega characterizes the imaginary axis. Okay, please remember that. This is important for us even when we go to frequency response analysis. Okay? So what we do is that if you and I want to find out these potential crossover points, in the closed loop characteristic equation, 1 plus g of s h of s, we substitute s equals j omega and then like figure out whether there is any potential solution, right, which is reasonable for a crossover point. Okay, so let's do that in this particular example. So for us, if you recall, the closed loop characteristic equation is 1 plus k divided by s squared plus 4s equal to 0. S squared plus 4s plus k equals 0. So what we do, we substitute s equals j omega. Now, when we substitute s equals j omega, s squared becomes minus omega squared. Why did we get minus omega squared? J squared omega squared, right? J squared is minus omega. So that's how we got minus omega squared. Then we had plus 4j omega plus k. So if we rearrange, we get this. Okay, we combine the real part and the imaginary part. Now, at first glance, one may think, oh, okay, look, I have only one equation, but two unknowns, right? What are the two unknowns? Omega and k. But then it so turns out that, this equation is a complex equation, right? So when we have a complex equation or complex expression being equal to 0, both the real part is 0 and imaginary part is 0. So that's why we get these two equations, right? So minus omega squared plus k is the real part. That is also 0. 4 omega equals 0, that is also 0. So from the second equation, you and I get omega equals 0 as a potential crossover point. And we substitute into the first equation, k equals 0 is the solution. So what it means is that, how do we interpret it physically? In this particular example, when we plot the root locus, if you recall, there are two open loop ports, right? One at -4 and one at 0. So when k is 0, one branch starts like this, another branch starts like this. So there is only one crossover point. That is, when k is 0, the one branch starts at the origin. Beyond that, the two branches of the root locus never go into the RHP, which is very good result for us, right? That means for every value of k greater than 0, you and I know that the closed loop system is stable. Of course, you and I would have already derived it in stability analysis, but we are still figuring out from root locus. I hope this step is clear. Okay, so in this particular example, k equals 0 is the only, or s equals 0 is the only crossover point, and which is where one of the branches starts off. Okay, I hope this step is clear. All right. Okay. So I hope it's clear what is the purpose of calculating the crossover point and what do we interpret from this step. Right? Any questions on that before we put everything together and then we come to the main observation of how the root locus is helpful to us? Okay, so now let's put everything together. We have drawn the root locus plot down, but let me draw it now. Okay, so we know that there are two asymptotes, plus or minus 90 degrees at -2. Coincidentally, -2 is also the breakaway point. Okay, this is a very special example. Okay, please note the point of intersection of the asymptotes and breakaway point need not be the same. Okay, in this particular example, they happen to be the same. Okay, so what happens is that one branch starts from here, one branch starts from here. When k equals 4, we have a breakaway point at -2. And then as k tends to infinity, the two branches of the root locus go along the two asymptotes to infinity in the S plane. Okay, so this is the root locus for this particular example. Okay, so please note, when we construct the root locus, you and I need to show what are the limiting values, directions at k equals 0 and k tending to infinity. We should also clearly mark the intersection of asymptotes, breakaway point, break-in point, and the corresponding value of k, and crossover points and the corresponding value of k. Okay, the root locus point. And we should also show these arrows. Okay, the arrows indicate how the root locus, the roots vary as k varies. Okay, that is also an important expectation of a root locus. Okay, this is how we calculate the root locus plot. And now from the root locus, you and I can immediately say that the closed loop system is stable for all k greater than 0. Obviously, we got that result from the Routs criteria before itself, right? But you and I can reconfirm it. Why? Because there are two branches in the root locus. For any k greater than 0, where do the two branches of the root locus lie in LHV or RHV? If you look at this graphic,
LHP only, sir.
LHP, right?
Yes,
So,
Philip.
please note, each branch of the root locus characterizes one closed loop pole, right? So, if both branches of the root locus lie in the left of complex plane, that means that both the closed loop poles are at the left of complex plane for all k greater than 0. So, that means that the closed loop system is stable for all k greater than 0. Okay, so I hope it's clear how we got to this conclusion from this particular example. Okay. Any questions before we go to the last concept for today? All right. So now I made one. Yeah. Yes, please. Any questions?
Sir.
Sir, this question might be very basic, but
Ah.
why do we have to go along the asymptote when we are going for k greater than k tending to infinity? I'm sorry. I'll
So
ask this again.
no, that is the definition of the asymptote. Say plane. Okay. Asymptote means you go along the direction. All right. Yeah. That is the definition of asymptote, and that is how we have calculated it. Okay. Yeah.
Because we are going from a pole to a 0, so it has to go along that direction. Am I
So,
right? Yeah.
the interpretation is that since there are not enough open loops, see, when do we have asymptotes? Only when m is less than n. So,
Correct.
bottom line is that you and I do not have enough open loops where the branches which start from an open loop, or we don't have enough open loop zeros, right? Where
Correct.
a branch starts from an open loop pole can end. Okay, so consequently, that is why we are going to infinity along the symptom. See, there is one subtle thing there, Prem. Okay, so once again, why this is along infinity. So once again, if I have to go back and share the subtle notions, let's say I go back to this example, right, which we already looked at. Now, what is the value of n here?
N is 2.
N is 2? No. N is
No, for which example? Oh, this example. Okay.
This particular example. Sorry. Let me put a box around it. The
Yeah.
general one which we calculated for.
Three.
I'm
sir,
sorry.
three, sir.
N is 3 because denominator polynomial is of order 3, right?
Yeah.
Then what is the value of m?
1.
1, right? So if n is 3 and m is 1, right?
M less than n.
Now we have a case m less than n. So obviously, two branches are going to go to infinity along
Asymptote. Yeah.
now, why is this infinity? The subtle point there is the following, right? Just for the sake of argument, right? You and I can write it as 0s plus 1, right?
Yeah,
0s
into 1.
so just to make the number of factors equal in the denominator and the numerator, I'm just doing this, right? So yeah. Now, at a conceptual level, right? We are having n equal to m, right? So that is, I hope you get the subtle point, right? So that is, we want to ensure that there are as many zeros or as many points where the branches, each of the branches will end, right? So,
Understood, sir.
so for these two things, what is the value of 0? It is as if they are at infinity. That's why they are asymptotes, right? So I hope that subtle point is clear. Okay. Yeah.
Got it, sir.
Yes, sir.
Yeah. Any other questions?
We can continue, sir.
Okay. All right. So now coming to the last concept. So if you recall, even when we looked at a proportional controller, right? I commented that, okay, look, when we do stability analysis, in this particular problem, we narrowed down, right? From minus infinity to plus infinity. And then we saw that for stability, Kp should be between 0 and infinity. Then for performance, we go further down, right? That is where root locus comes in, right? And helps us. So can we narrow it down to a smaller range? So now, if you recall, we constructed settling time less than 4 seconds, peak overshoot less than 10%, right? The corresponding closed loop pole region required for that, right? So where we want to ensure that the closed loop system satisfy the performance, these two performance requirements. And if you recall, the corresponding open trapezoid was this, right? What I am retracing here, right? Now, if a system needs to satisfy both performance and stability and performance, we already saw that for all k greater than 0, the closed loop system is stable. Okay, so that is understood. But if I want to satisfy performance, what is it that I need to ensure? I need to ensure that both the branches of the root locus in this particular example should lie within this open trapezoid, right? Now, how do I calculate it? So please note that this branch from -4 starts within the trapezoid, but the other branch starting from 0 starts outside the trapezoid, and it comes within the trapezoid only what we label as point A. So I need to find out what is the value of k at point A, right? How do I do that? Once again, we use the closed loop characteristic equation. Okay, so closed loop characteristic equation is the equation that relates the S value of k and closed loop poles, right? From here, we get this formula, right? If I rearrange it, k is minus s squared plus 4s. So if I substitute s equals -1, which is this point, I get k to be 3. So what does this imply? When k is greater than 3, both branches come into the open trapezoid, right? That we have. I hope this step is clear. Okay, please ask me any questions before I move forward. Is this step clear to everyone? We are going step by step. Okay, there are two branches starting, one at 0 and one at -4. The branch starting at -4 is remaining in the initial phases within the open trapezoid, but the branch starting at 0 enters the open trapezoid only when it hits the -1 point, right? As we can see graphically. And so consequently, we found the value of k to be 3 at the -1 point. Okay, when s equals -1 for this particular closed loop system. Okay, using this equation. I hope this is clear. But do the two branches remain within the open trapezoid for all k greater than 3 to infinity?
No.
What happens? When do they go outside the trapezoid?
If the in
Insert करते
imaginary
हैं. So
axis
let's
length
say
is
I have inserted
is falling
this
away
bolt
out of the boundary, like
So,
inside
10. Okay.
yeah, please go ahead, Roshan.
2
okay
into 10, 57.33 degree. Beyond that length of the, it will go outside of the boundary.
So let me zoom in and explain here.
all right.
So please note, one branch is
Now you
coming like
can
this.
see
It
that
hits break.
one
It
end
hits.
of
They intersect at -2, and then both the branches go like this along asymptotes, right? Now, what we have labeled as point B and point C. Beyond that, the two branches go outside the trapezoid. That means beyond that, the peak overshoot condition is not satisfied, right? Because we want both settling time and peak overshoot to be satisfied. Is it not? So at points B and C, I'm having the performance condition not being met beyond those 2 points, right? When the root locus branches go outside the trapezoid. So I need to find out what is the value of k at B. For that, I need to find out what is the value of S at B. So say the value of k at B and C will be the same because of symmetry. Okay, because we are dealing with the polynomial with real coefficients. Roots will be complex conjugate. So poles, close to poles are also complex conjugate. So if you find the value of k at B, it will be the same as finding the value of k at C. Okay, that symmetry holds. Okay, please note that B and C are complex conjugate points. So how do I find the value of S at B? So it is going to be, the real part is going to be -2. What is the imaginary part? You look at this right triangle, right? This angle we found to be, oops, sorry, what happened? Oh, sorry about that.
57.33, sir.
This. Where it's, yeah, here it is, right? This angle is 53.7. This adjacent side is 2. So this is going to be 2 tan 53.7. Okay, so the value of S at point B is -2, which is the real part, plus 2 times 53.7 times J. Okay, so I'm writing it this way. So that's what you and I do here. So we go and find what is the value of S at B. Then we go and substitute that value of S into this equation for K. We get the value as 11.45. Okay, you may think, hey, look, oh, the value of S is complex. How do we get a real number? Okay, so that's how it is. Okay, so we get a real number for this. All right. So that's how you and I go and calculate this value of K at B. And the value of K at C is going to be the same, okay, as otherwise, right? So essentially, we are going to have, the value of K at the point C is going to be 11.45 also, okay? So what can you and I interpret? That is the performance requirements as given for settling time and peak overshoot as specified by this open trapezoid is satisfied only when both branches of the root locus lie within this open trapezoid. And that happens only when K is greater than 3 but less than 11.45. So you can see that you and I have reduced through this analysis the potential region of K or KP, right, in this particular example, right, where you and I need to go and fine tune from -infinity to +infinity. Using stability analysis, we found that KP should be positive. Then performance analysis and root locus, we even narrowed it down to 3 to 11.45, right? And that is what is shown in this graph, right? The feasible region should be greater than 0 for stability, but then we narrowed it down to 3 to 11.45 for both stability and performance. And I hope this demonstrates the usefulness and the application of the methods that you and I have been learning. Imagine that this is a system for a motor which is being used, let's say, in the steering system or a traction motor and so on, right? We are asked to design a proportional control, right? Then what happens is that we are essentially going to have to tune KP between 3 and 11.45, which is a big relief rather than tuning from -infinity to +infinity, right? So I hope this demonstrates the application and the usefulness of this particular method. Okay,
Sir, I have a question over here.
no.
Suppose if I'm not aware of root locus method for finding this range of KP over here or K over here, so I can do this problem in a trivial way that you have taught us in the previous class, that if I express this and compare it with the standard y double dot plus 2 into xi into omega n y dot plus omega n square, and if I compare that coefficients and express the k in terms of xi in terms of k, and then apply the MP formula like e to the power minus pi into xi divided by 1 minus under root 1 minus xi square should be less than 0.1. So by that also we will get the value of k. Is that right, sir?
Please try out, scan the solution and tell me, Roshan. I want you to figure it out yourself, right? Please note, I have only 2 comments which will serve as hints for you for the method that you have proposed. Very good thought process, right? But what will happen is that I have only 2 comments, right? Let's say in this particular example, you and I are dealing with a second order system. But please remember, the performance specifications are derived based on dominant second order systems. So in real life, you may have a 5th order system. Then the method that you are discussing may not work out. Okay, root locus will be more powerful. Okay, point number one. But having said that, let's stick to this second order system. Okay, we have only this particular example. Let's say we are always going to encounter only second order systems in real life. Let's talk with that perspective. What you are proposing is a very nice thought. Please try it out. What you will get is that you will get only the limiting value of k where it hits this thing. Okay, so but then you and I want a range, right? Please note, like all these are approximations of reality erosion, right? See, who said a traction motor or a steering motor should be a linear timing variant, second order underdamped system, right? You and they are approximating it as that, right? So that is why in these methods, we want to get a range of parameters in which you and I will go and tune and then find the best possible value. Okay, so that is the second point I will give as a response to your question. But good thought process. Please try it out. Okay, and show me what you got.
Okay, sir. Thank you so much.
Sir,
Yes, please.
so here, if we see the root locus, means whatever we have drawn in green arrows. So one of the portion of the locus is -4 to 0, -4 to 2.
-4 to -2. Okay.
-4 to -2. Yes. So
Ah.
this portion is entirely into the trapezoid.
Yes.
So means how do we interpret that this k0 to k is equal to 4 lies within the stability as well as performance requirements?
So see, because we should not interpret it that way. Because see, please note, I'm repeating again. All branches of root locus. The keyword is all. Okay. All branches of the root locus should lie in left off plane for stability. All branches of the root locus must lie in this open trapezoid for performance. Okay. It so happened that, let's say, we call this as branch 1. Okay. And this is branch 2. What you are saying is that, look, hey, you know what? The portion of branch 1 on the real axis always within this open trapezoid, right? Does it mean that it satisfies performance completely? No, because why? One half of branch 2 lies outside the open trapezoid. Okay, that is why we figured out k greater than 3 as one limit. I hope that answers the question. Okay.
Clear, sir. Okay, yes. Thank you, sir.
Okay, I think it's almost 5:55. Arnachalam, is everyone present today? No, sir.
Sir, only one absent, sir. Hemant.
Hemant alone is absent. Okay, so everyone else is present. Is it? Hello?
Yes, sir. Yes, sir.
Okay. Yeah, I'll mark attendance there for everyone. So we will continue from here. Okay. So if there are more questions also, we can continue from here. In tomorrow's class, we look at what happens with positive feedback. We will learn what are the complementary steps. Then I will give you homework problems also, through which you can do things and then like figure things out. Okay. Yeah. All right. So we will continue from here tomorrow. So any further questions also, we will discuss them tomorrow. Yeah. Fine.
Thank you, sir. Thank you so much.
Thank you, sir.
Bye.
-2, -4.
Thank you, sir.